everyone. We are a small but mighty group today. I wish you all the best with your upcoming test. Who has physics as well this weekend? Okay, almost everyone. So you're learning to multitask, you're learning to take on good challenges, and I'm sure you are gonna rock this weekend. So we have been sending some important OWL announcements. Make sure you're checking those details, like what to bring for the test. You can look up on OWL grades to see where you need to write. If you write with accommodated exams, go to the room that they tell you to go to rather than the one we share with you on OWL. Academic integrity is very important. We want to become scientists and professionals who are trustworthy and have earned and worked towards our grades, that people can trust the science that we do, the articles that we publish, and we practice that in undergrad as well. So during this test, make sure you are practicing integrity, doing your own work, not looking at the people around you. We had an OWL announcement about that today as well. Just focus on your own stuff, and that's great. It's not worth cheating and having an investigation and something added to your academic record. So always make sure you're doing your own work, and you'll save me a lot of paperwork as well. As well, the tests in university are timed. So we have a start time, we have an end time. At the end time, the proctors will tell you it's time to put down your pencils and stop. The test time for chemistry includes the time to fill out your bubble sheet. So that means you don't get extra time to fill out your bubble sheet. Don't leave filling out your answer bubble sheet to the end of the test. That can lead to very troublesome problems. Can you imagine what could happen if you did your whole test but you forgot to write your answers on your bubble sheet? We have to only grade your bubble sheet. Okay, so make sure your answers are transferred to your bubble sheet well before the end of the test. Do not leave it to the end. And plan your time. The tests aren't meant to be stressful for time. You should have good time. But sometimes people can encounter little pitfalls, so they get stuck on one question. They're like, I'm going to do this until I get it. And all of a sudden they look up and they've been on one question for 30 minutes. Don't let that happen to you. Think about how much time you have, how many questions there are on the test. It's similar to last year. And calculate your time per question so that you don't get sucked into the trap of focusing on only one question. Okay, we're going to start with a question here today. Which of the following would not be a fair question from Chapter 1? Chat with the person beside you and submit your response. The ... tells you the question continues. And I'll give you 10 more seconds. And 3, 2, and 1. Okay, almost 90% going for C, and I agree. Why? Well, that would be a good question from perhaps Chapter 2, but not from Chapter 1. So that means all the other questions up there could be reasonable questions. When you're doing your final studying, go through Chapter 1, look at what those headings are. Think if I was the professor and I had to write a question based on something in this section, what would it be? You come across topics like mass percent. Things like how many moles is required to make a solution of a particular concentration. How many grams will form during this reaction, thinking about limiting reagent and percent yield. What's the pH of a solution prepared this way with a strong acid or a strong base? So these are all concepts that you can get from the headings in Chapter 1. So make sure you review that so there aren't any surprises. Okay, next question. Look at figure 2.1.7 in your workbook. Which of the following could be a question based on that one. There we go. Based on that figure, which is false?
Last year I checked the test and there were some questions like on the course outlines on the test. So are you getting questions?
Ooh, no. Sorry. .1.17. Okay, and just to help you out there, 2.1.17 is what we're going for there. Thank you very much. You could answer the question without the figure, but the figure is certainly helpful. Thank you very much for that. So figure 17. And 10 more seconds.
Which one's false?
And 3, 2, and 1. Okay, so we're quite split here. Here, the majority is not actually winning, so there is an incorrect statement from A to D. It's C. Why? Well, when you're looking at that figure, 17, it's written on a 2D piece of paper, right? So the PZ orbital, the third one, is supposed to be coming straight out of the page towards you and away from you. So we have a px along the x-axis, a py along the y-axis, and a pz pointing straight towards you. But we can't really draw it like that on a 2D piece of paper. So the z is shown like on a diagonal, but it is actually on the z-axis. So px, py, pz, px, py, and pz are all orthogonal. They're all 90 degrees apart from one another, okay? So that one is false, which means the 2p orbital has two phases, the red and the blue, or the up and the down on that wave function. Finding the electron at the nucleus, we can see the probability density function shows a node there. We have a nodal plane, and so we're not going to find the electron when we go from the positive phase to the negative phase. And we do have three orbitals, px, py, and pz, that all have the same energy. So that means they are degenerate. Any questions on that? Okay, let's keep moving along here. Okay, so we finished off at this problem last class with capsaicin. This is the molecule in hot peppers that makes it extra spicy. And here we learned about how carbons are implied. Every bend in a line and the end of a line, if there's no other atom written there, means we have a carbon atom. The next piece of the puzzle that we need to add is adding in the hydrogen atoms. Now, hydrogen atoms are implied on carbon atoms. We need to make sure carbon has a filled octet. Based on its place in the periodic table, it starts with 4 valence electrons. So it could form 4 single bonds, 2, 4, 6, 8. That would give it a filled octet. 2 double bonds, and a few other combinations there. If we don't see anything else in the structure giving carbon a filled octet, we assume there are hydrogen atoms there helping it to fill its octet. Hydrogen atoms are only implied on carbon. Notice here next to the oxygen, we had to write in that hydrogen. Next to this nitrogen here, we had to say there was a hydrogen. We don't imply them on anything else except carbon. So we're going to start on the far right side. The carbon at the very end of the molecule, we can see it has 1 single bond. So therefore, it must have 3 hydrogen atoms filling out that filled octet. Okay, then the next one down here, it has 1 carbon-carbon bond, and so therefore, it must have 3 hydrogens. The carbon next along the chain here, we can see it has 3 bonds to carbon. That would get it to 6 valence electrons. We need to add in a hydrogen there. The next carbon has a double bond. So that's 2 4 electrons there, plus a single bond, which leaves us with a spot for 1 hydrogen. The next carbon to the left of that has a double and a single bond already, giving it space for 1 more hydrogen. The next carbon that has 2 single bonds, to get it to a filled octet, it can have 2 hydrogens. And the next one as well, 2 hydrogens. And the next one for the same reasons, 2 hydrogens. And the next one. Okay, what about this carbon that has a double bond to oxygen? Show me with your fingers. How many hydrogens does it have implied? 0, that's correct. It already has a single bond, that's 2 electrons, another single, and then a double, that brings it to 8. So we don't need to add anything else. The next atom is a nitrogen, so we move along to the carbon where we can see we need 2 more hydrogens. Then the next carbon here has a double, single, single. That brings us to a filled octet. And I'm going to go clockwise down to the next carbon. It is a double single, so we add 1 more hydrogen. The next one, a double single, and add another. The next carbon has 2 singles and a double. It already has a filled octet, so we don't need to do anything else. Same with the next carbon as we go along. A double and 2 singles, it's done, which leaves us with the final carbon there. Okay, so we have added in all of our hydrogens, and the final piece of this puzzle is to add in the non-bonding electrons. It's important to add these and know that they're there when we get to topic 3.2 and talk about molecular shape. Often they're not drawn in line diagrams because the people interpreting these molecular structures most often know how to figure out if there are non-bonding electrons there. So as scientists, we need to know how to read that and interpret those implied non-bonding electrons. Okay, so for all of the carbon atoms, they all have a filled octet. They don't have any non-bonding pairs of electrons in this structure. It can happen, but it's not very common. So we want to look at the oxygens and the nitrogens there. I'm going to look in the middle of my molecule here. I see that oxygen that has a double bond. The double bond has 4 electrons in it. We need to get oxygen to a filled octet. That means I need to add 4 more, or 2 pairs of non-bonding electrons. I'm now going to go to the OH on the far bottom left side of the molecule. That OH means there's a single bond holding oxygen and hydrogen together. I can also see there's a single bond from oxygen to carbon. That gets me to 4 electrons, but I need to get to 8. So I can add 2 non-bonding pairs of electrons to give it a filled octet. Now we'll go to the OCH3, and I'm going to redraw that above. So OC, and then 3 hydrogens on the carbon. So we can see the carbon in the middle here has, the carbon in the middle as we've drawn here has 3 hydrogens and a bond to oxygen. That has a filled octet. But the oxygen has a single bond to carbon, a single bond to carbon, but we need to get it to a filled octet as well. So we're going to add 4 more electrons, or 2 non-bonding pairs of electrons to fill that out. And then we can go back to the middle of the molecule. We have a nitrogen and hydrogen. And that nitrogen, I'll just circle it right here, has a single bond to carbon, a single bond to carbon, and a single bond to hydrogen pointing down. That gets it to 6. We need to get it to 8, so it has a non-bonding pair of electrons there. Okay, and I think that exhausts everything. We've made all the implied explicit, and we've drawn them in. We need to know how to interpret that, and these pieces are going to become very important when we go from Lewis structures to Vesper shapes, which is what we're going to do right now. Okay, so we are ready to move on to 3.2, looking at valence shell electron pair repulsion. Lewis structures tell us single bonds, double bonds, triple bonds. They tell us non-bonding electrons. They tell us formal charges, but they don't tell us anything about shape. And molecules exist in three-dimensional shapes. And the shape of the molecule, whether that bond points this way or that way, can change the way that it interacts with other molecules. On the left here, we have the Lewis structure of water. And that is correct. We can see oxygen has 2 non-bonding pairs of electrons. We can see it has 2 single bonds to hydrogens. And it looks like the bond angle there from hydrogen to oxygen is 180 degrees. It looks straight. However, we can't interpret shape from a Lewis structure. We have to add Vesper theory onto it, and that tells us that water actually has a bent structure. How do we know that? Well, it's Vesper theory. Remembering what the title Vesper stands for tells you what the theory means. So we are talking about the valence shell electrons. That's all we've been doing in 3.1 as well. It's the valence electrons and the highest principal quantum number that participate in bonding. So it's the valence shell electrons. We're talking about them in pairs, so non-bonding pairs of electrons, then there are the 2 dots, a pair of electrons to make a covalent bond. And these electron pairs repulse one another. They try to get as far away from one another as possible. If you can remember what Vesper stands for, you're on your way to explaining Vesper theory. So, what is the tenets of Vesper theory? Well, we're talking about electron pairs in the valence shell. We already know that from the title. We're talking about electron pairs, yep, and they repel one another. And they repel one another in 3 dimensions. So they use up all the space that they can. Sometimes we feel like we're tied down to a 2-dimensional piece of paper, but molecules move in 3 dimensions. That's why the model kits are really handy, because model kits help us visualize things in 3D. Now, this piece of the puzzle, number 3, isn't quite explained in the title. And this tells us that lone pairs of electrons, when we have those 2 dots together, they repel just a little bit more than bonding electrons. Why? Well, bonding electrons in a covalent bond, they are shared between 2 atoms. So 2 nuclei are being attracted to those electrons. For a non-bonding pair of electrons, they're attached to only 1 atom. And so they take up just a little bit more space. Lone pairs of electrons repel other pairs of electrons just a little bit more. So we're going to see bond angles impacted by whether we have a non-bonding region or a bonding region. The bond angles will be pretty similar, but we'll have it just a little bit bigger or just a little bit smaller depending on where those non-bonding electrons are. And then finally, multiple bonds are treated as a single region of electron density. So if we have a single bond or a double bond or a triple bond, for Vesper theory, we don't really care. We're just saying that's a bonding region. We're going to see later on that it's because it has a sigma bond and a pi bond. For now, we just need to know that a bonding region is treated as one region where electrons hang out. So when we're talking about shape, we have this handy little short form notation to be able to communicate regions of bonding and regions of non-bonding. And when we know this ax notation for a molecule or a compound, we can predict its shape. So A is telling us about the central atom. That's our reference point. So for water, oxygen would be our A. We just call it A. Then we have X, the number of atoms or bonding regions around the central atom. We just call it X. We don't really care if it's fluorine or hydrogen or whatever. What we care about is how many there are. And M tells us the number of bonding regions, or the number of atoms, because every atom has to have a bond to that central atom. Then we have N, and this tells us the number of non-bonding regions, and that's designated by E. So as we look at this example of water, I can see it has 2 non-bonding regions of electron density. I see 2 pairs of non-bonding electrons. So if I want to write out my ax notation, A is the central atom. I'm interpreting that as oxygen. E is the number of non-bonding regions. I can see that's 2 here. So the number of bonding regions, I have 1 bond to a hydrogen and another bond to a hydrogen, and that tells me I have 2 bonding regions, or 2 atoms that are connected to the central atom. So this water molecule could be classified as an AX2E2 molecule. 2 regions of bonding, 2 regions of non-bonding, which means it has 4 regions of electron density. We can take the sum of M and N and know where to categorize this molecule based on how many regions of electron density. Okay, so we're going to practice that on this molecule here. This question asks us how many regions of electron density does each atom have in this structure? And then I've added a little tip below. Whenever you have to do this type of problem, you need to know the non-bonding and the bonding regions. We need to remember that hydrogens can be implied and non-bonding electrons often are not written down for us. So before we start counting, we want to add in all of these implied regions. So I'm going to start on the far left with nitrogen with a triple bond. The triple bond takes up 6 electrons. I still need 2 more to get a filled octet. So that means this nitrogen has a non-bonding pair of electrons. I'm going to continue along to the end of that triple bond. That tells me there's a carbon atom there. This carbon atom has a triple bond on one side and a single bond on the other. That gets it to a total of 4 bonds, or a total of 8 electrons. That has a filled octet, so I don't have to worry about any hydrogens or non-bonding electrons. The bend in the line, that's another carbon atom. I can see it has a single and a single bond. That means it has room for 2 more hydrogens. The next atom is a carbon. It has a double bond to oxygen. This carbon has a total of 8 valence electrons already. So going down to the oxygen with a double bond, the double bond gets it to 4 electrons. We need to get it to 8. So we can add 2 pairs of non-bonding electrons. Going back to the carbon, we can see it has a single bond to a nitrogen. I'm going to draw this nitrogen off to the side. When it says NH2, that means it has a single and a single bond to hydrogens. And then, of course, that single bond to carbon as well. It's sometimes helpful to draw out that fuller structure so that you can see where the bonds are and you can more easily count and see that nitrogen needs to get to 8, which means we need to add a non-bonding pair of electrons. Okay, so we've drawn in our non-bonding electrons, we've identified where our implied hydrogens are, and now we're ready to count. So I'm going to go back to the left-hand side of the molecule to nitrogen with a triple bond. I can see it has a non-bonding pair of electrons and a bonding region of electron density. This counts as 2 regions of electron density, 1 bonding and 1 non-bonding. So then we go to the next carbon. It has 1 bonding region and another bonding region. That gets us to 2. The next carbon here, we can see it has 4 single bonds, which gives it 4 regions of electron density. Continuing on that carbon chain, the next carbon has a single, single, and double. Show me with your fingers, how many regions of electron density? 3, excellent. Okay, let's go to that bottom oxygen. It has a double bond and 2 non-bonding pairs of electrons. Show me with your fingers, how many regions of electron density does it have? Okay, I agree, it has 3. And now we get to our next nitrogen, our amine here, NH2. Show me with your fingers, how many regions? And 4. Okay, I wasn't tricking anyone here. So definitely 4, 1 non-bonding and 3 bonding regions of electron density. Excellent. Okay, once we know how many regions of electron density we have, then we can turn the conversation into a 3-dimensional shape. When we're talking about 3 dimensions, that means we need to get off of our flat piece of paper. And so sometimes we need to tell you something's coming towards you. If something is coming towards you, those lines are called wedges. And imagine if something comes towards you, it looks like it's getting bigger, it's coming out to give you a hug or something. So when we have these solid wedges, that means it's coming towards you. If we have a plain old line that's flat, that's showing you that it's just in the plane of the paper, so it's flat down here. The wedged line shows you that it's going away from you, so it's going off into the distance. So we could draw this molecule here, where we have the carbon atom on the left, with this hydrogen coming towards you, 1 going away from you, and 1 right in the plane of the paper. And we'll build this for next class. Okay, once we have figured out the number of regions of electron density, we can move on to the electron geometry. We're going to build lots of molecules as we're going across and talk about their different shapes. Electron geometry informs what the molecular shape of the compound is. It's not necessarily the same term. The molecular shape is built off of electron density regions, but if some of those regions are non-bonding, then the molecular shape is going to be different from the electron geometry. And this will become apparent as we go across. So if we want to figure out the shape of a compound, we start by drawing the Lewis structure, and we know how to do that already. That tells us where the bonds are and where the non-bonding electrons are. Then we figure out the electron arrangement and count how many regions of non-bonding versus bonding. Once we know how many regions of electron density we have to see which of those are bonding versus non-bonding, and we can draw a conclusion on its molecular shape. And we're going to go through this step by step, starting with 2 regions and working our way up from there. So let's start with the simplest example when we have 2 regions of electron density. Now, I hope you brought your model kit with you today. And now when you open up your model kit, it comes with all sorts of cool pieces. If you did not bring your model kit today, we're just going to introduce it, but we're going to be using it a whole lot come next class. So definitely bring it with you next week if you didn't bring it today. Now when you open your model kit, you're going to see long, flexible pieces with a whole bunch of little black pieces on it. If you look closely, they have little labels. This one says SP3, and we're going to talk about what these labels mean as we go along in the course. But we're going to sometimes use the black pieces here, and they have a particular bond angle. Sometimes we're going to use the gray pieces, and you can see if you lay them over top of one another, the bond angles are just a little bit different. Sometimes you have different colored pieces, and we can use these to indicate oxygen or nitrogen. You have some double bond pieces, you have a triple bond piece, and you have some funky color pieces. And I would like you, actually, let's go back for a second. Why don't we build this one? Let's go ahead and build this one. So I would like you to grab 2 black pieces and put them together until you hear a click. And then grab 2 more black pieces and put them together until you hear a click. Now you'll notice some of these have a prong end, a pointy end, and the other ones have a little hole. So you can put these together by putting the pokey end into the hole. And here I have just made an ethane molecule, and you can too. So I have my carbon and my carbon. Connected to this first carbon, I have 3 hydrogens. Connected to this carbon, I have 3 hydrogens. If I want to make the molecule that I have on the other screen over there, I could add an oxygen. I'm going to say this is my oxygen and this is my hydrogen. And now I have made ethanol. So notice that this kit is kind of fun because you can hold one group and it spins. And single bonds, you can rotate those single bonds. We're going to see when we get into some stereoisomers, double bonds don't rotate so well. But single bonds certainly do. So if you have this with you today, see if you can align your structure to exactly match the one on the page. So here my carbon atoms are held in the plane of my page. I have this hydrogen coming towards me and this one going away from me. I'm going to rotate the right-hand side to have the oxygen in the plane of the page, the hydrogen coming towards it here, a hydrogen coming towards me, and a hydrogen going away from me. So if you have built it, you can look at all of the bond angles and see how it rotates. You get to bring your model kit with you into your tests and exams in this course. So learning how to use it is going to be super helpful come test 2 and our final exam. So again, bring it next week if you don't have it with you today. Okay, we're going to start with 2 regions of electron density. You should have 2 of these pieces in your kit. This is the center atom. This is our A. And this is an atom it could be bonded to, and another atom it's bonded to. You have a bunch of these little balls in your kit, and you'll notice that they have a thin end and a thick end. So sometimes you can put the balls on the end to distinguish different types of atoms. So I'm starting here with an axe notation where I have my central atom and it's connected to 2 other atoms. We can measure the bond angle, and you can see even without a model kit for this one's pretty straightforward, that it has a bond angle of 180 degrees. And this is by far the simplest structure that we can have. When the number of bonding and non-bonding regions is 2, we have a linear shape. It's going to get more complicated after this, but let's start with our linear shape. So what's an example of a linear structure? Actually, I'm going to go back for 1 second. We can use this axe notation here to give a better description of this compound. A is our central atom, and here I'm going to say we have 2 atoms connected to it. So 2 bonding regions and 0 non-bonding regions. If one of these was a non-bonding region, you wouldn't really be able to measure a bond angle for this one, right? For a bond angle, you need a point, a center point, and another point. So for this example, we really only have AX2. We could say the non-bonding regions are 0, but we don't usually write the zeros in, so we could just call it an AX2 type of molecule. As soon as we know I have 2 regions of electron density, both of them are bonding, we have a linear shape. So let's go ahead and draw an example of a linear structure. We're going to start with C2H2. Now, some of the examples that we're going to do in 3.2 will draw the Lewis structure, and sometimes we're not going to bother because we have talked about Lewis structures already. That said, we haven't done many triple bonds, so we're going to start there today. So, carbon has 4 valence electrons. There are 2 of them. And I have 2 hydrogens, each with 1 valence electron. And that gets me to 10 electrons. Now, the carbon and carbon are going to have a bond. Hydrogens are terminal atoms, so they have to be on the end. We can't put hydrogen in the middle. So therefore, we have to at least have this skeleton structure. Now, I have 10 electrons, which tells me I have 5 pairs of electrons. I've used up 3 already for my skeleton structure, which leaves me with 2 non-bonding pairs of electrons. So I'm going to put one of those non-bonding pairs on my carbon and another one on the other carbon. Hydrogen has a noble gas electron configuration. It can claim 2 electrons. But my carbon atoms right now, they only have 4 electrons that they can call, 6 electrons. Single bond, and non-bonding. So we're going to need to share some of these electrons to give each atom a filled octet. If I turn that into a double bond, that's a step in the right direction. But if we turn this into a triple bond, we can see each carbon can now claim 8 electrons. So we've drawn the Lewis structure. That was topic 3.1. But now we can predict its shape. And we can predict its shape around either carbon as our central atom. It doesn't really matter. So here I'm going to choose the carbon on the left. I can see it has 2 regions of electron density, a triple bond and a single bond, but we call it bonding region 1 and bonding region 2. Now, these electron regions are going to try to get as far away from one another as possible. If they look like this, they're way too close. 90 degrees, still too close. If we get them 180 degrees apart, that's as far apart as we can get these bonding regions. Electron pairs repel one another, and so they get as far away as possible, which tells us we have a bond angle here of 180 degrees. We have a linear molecule. At the other carbon atom, we could measure the bond angle there as well and see the single bond to hydrogen and the triple bond to carbon get as far away from one another as possible. So we can see that we have a linear shape at each of these carbon atoms. Linear is nice and straightforward. Let's make it a little more interesting, and let's move up to 3 regions of electron density. So now we have our central atom, and if we try to get 3 regions of electron density as far away from one another as possible, the best way that we can do that is to get them 120 degrees apart. You have a trigonal planar electron arrangement in your model kit. So you should have about 2 of these pieces. So see if you can find the one that looks like a triangle. Here we have the central atom, and we have 3 regions of electron density around it. Based on 3 regions of electron density, we can say that it has a trigonal planar electron geometry. Trigonal, because it's a triangle, it has 3 regions of electron density. And planar is because if you lay this on your paper, it's perfectly flat. We're going to see other structures aren't planar, but this one certainly is. So if we have 3 regions of electron density, we immediately go to trigonal planar electron geometry. But now we need to take this a step further, because depending on whether it's bonding or non-bonding changes the name of the compound or changes its molecular shape. If all of these are bonding regions, then we call this a trigonal planar molecule. However, if one of these regions is a non-bonding region of electron density, we have to give it a different name. That non-bonding region, I'm just going to choose this one for now. This non-bonding region of electron density, I'm going to cover it up with my hand, and this is a really helpful strategy for coming up with shapes. The non-bonding electrons still take up space. So I'm going to put in atoms here so we can distinguish my bonding from my non-bonding regions. So here I have a bonding region and another bonding region. I don't know, maybe it's carbon and chlorine, whatever. But now I have a non-bonding region of electron density. It still contributes to spreading out the electron density as far away from one another as possible. It still has an trigonal planar electron density arrangement. But if we want to give the molecule a name, the non-bonding electrons, you can't actually see them when you're looking at the shape and the bond angles. So if you were a ruler of the universe and had to come up with a name for this structure, green to gray to red, what would you call it? Yeah, you could call it bent. I mean, you could come up with a whole variety of names, but bent is a pretty good name. It almost looks linear, well, not really at all, but you could imagine someone came along and bent this bar. If you weren't able to see these non-bonding electrons, it just looks like a bent line. And whoever came up with this name was not very creative, and this shape is called bent. So it still has a trigonal planar electron geometry. When we found it out, it had 3 regions of electron density. We went to that trigonal planar, but its molecular shape is actually bent. So this one is an AX2E1, in contrast to an AX3. So AX3 is trigonal planar. AX2E1, when we have that non-bonding region, it's now just called bent. So let's do an example here. If we had BF3 and we wanted to figure out what its molecular shape was, well, the first step is to draw the Lewis structure. I've gone ahead and done that for you because I want to focus more on the shape. I could classify this structure as an AX3 molecule. I can see it has 3 regions of bonding and 0 non-bonding electrons. Now this might look a little funny. You may notice that boron doesn't have a filled octet. And that's the case. Boron is so small that sometimes it has molecules and compounds that it forms that it doesn't have a filled octet, and this is one of them. So it's an AX3 molecule. We have 3 regions of electron density. When we figured that out, we go over to our model kit. So far we have linear, 2 regions of electron density, and trigonal planar with 3 regions of electron density. All of these regions are bonding regions, therefore the molecular shape is trigonal planar. Okay. As we move along, we're going to move on to more regions of electron density, and the shapes and the bond angles become a little bit more interesting. So it's time to call it a day. I want you to have some extra study time. All the best with your test on Saturday. When you come back to class on Monday, please bring your model kit because we will be using it then. Have a great day, and I will see you tomorrow.